Thank you so much for inviting me to speak to this group. Um, I think it's a really fantastic organization that you've all been building here. I want to talk about some of the challenges of tipping points in the climate system and connect those to some of the economic impacts that I and colleagues of mine have been studying to understand really how climate change is going to impact people's lives and livelihoods. Just to give you a short preview of what this is going to entail, I'm going to be talking about the risks of climate change and what are called economic damages, what those climate change risks mean in economic terms. The climate system is being pushed to the edge of tipping points. I'm going to talk about what tipping points are and how they work. But tipping points will cause enormous changes in how the climate system functions. They're going to increase temperatures, they're going to cause additional sea level rise. They are going to make climate mitigation more difficult. And so that's going to have a lot of economic consequences and consequences for how we as people who want to act and make change in this area need to think about the climate system and our actions. First off, just a few points that I think are going to be familiar to all of you from the climate science. First, the climate is changing. It's changing rapidly, and impacts are already occurring on large scales. Some of my favorite examples, though certainly not good ones, are that the way in which coral reefs are dying the world over through coral bleaching, so that many scientists think that coral reefs are going to be in most of the world extinct in just a few more decades. The incredible heat waves that we've been experiencing in many parts of the world, like the one across India and Pakistan in 2019, one of the greatest, highest heat waves that has ever occurred in the historical record. The mega drought in the southwest of the United States, probably the largest drought there in 500 years and heavily driven by climate change. And the impacts of sea level rise that we're seeing in more and more low-lying regions, and they also are hitting regions that are right next to the ocean as they make every storm more powerful and more damaging. Greenhouse gases are going to continue, sorry, differently. If greenhouse gases continue at the rate that they've been going, the world is going to look very, very different in 2100. So we talk about this in terms of the business as usual scenario, which used to be called RCP 8.5, is now called SSP 585. And so just to give you one of my favorite examples of how that's going to change, if you look here, these are in the blue historical average summer temperatures for different states in the US. And so I'm speaking to you from Delaware, which is right here in the middle of the pack, with average summer temperatures around 76 or 77 degrees. By the end of the century, it's going to be hotter up here than any state currently is today. And that's not the least of it. As we all know, it's not just heat, it's humidity. And so this is how heat and humidity combine to create dangerously hot days that are the kinds of days that people end up getting heat stroke on. And so again, Delaware is right here in the middle of the pack. Louisiana is the hottest and humidest, most challenging state in the United States. By the end of the century, most states in the United States are going to be hotter and more humid than Louisiana is now. Delaware is going to, for example, go from having a few of these dangerously hot and humid days a year to basically having a month or two of them every year. And that's just a small example. Um, Addressing climate change is going to require strong action for both mitigation, that is reducing carbon emissions, and adaptation. It used to be that people talked about these as one or the other. We're going to have to do both because the world is going to change no matter what we do. But by acting both, thinking large about how our energy system works and thinking local about how to protect our communities, we can make it through this. Although I think a lot of people are aware of this, often we don't talk very much about the uncertainty of climate. Uncertainty is just a fact of climate change, and I'm going to be talking about a lot when in talking about tipping points. Just to tell you how we often think about this, scientists, we use these shared socioeconomic pathways, which are scenarios of how emissions could go in the future. And so two of the big ones are SSP5, this fossil fueled development, where CO2 emissions just keep rising, and SSP1, sustainable development, where we turn it around and go to first net zero globally by in about 50 years, and then actually negative emissions for a while after that. Now, I tell you that so that I can show you the way that those emissions are going to turn into temperature changes. We often think of this SSP1, that low emissions scenario, as meaning that we can keep the world at no more than 2 degrees Celsius of warming. But it's unfortunately not true that we can guarantee anything like that. If we go on that very strong mitigation pathway, we're going to be keeping ourselves within a range of temperatures, and we don't know exactly where we're going to fall. In fact, you look across the models, we could end up anywhere between 1.5 degrees by the end of the century to 3 degrees, and 3 degrees of warming would be disastrous, and we can't rule it out. But if we don't make the changes that we need to make, we're going to end up on, for example, this red fossil fuel development pathway, where we could have between 3.5 and 7 degrees of warming, which would cause many parts of the world to become essentially uninhabitable. So these are very dangerous kinds of uncertainty. So why does uncertainty happen? We're moving out of the historical record. We're moving out of the data that scientists need to use in order to understand the world. As a result of that, a lot of the processes that happen in the climate just need a lot more study, a lot more understanding. For example, scientists are struggling right now with how to understand cloud formation and the energy transports in the ocean. But there's a long list of these processes that we don't understand. The rate of change of how slow-moving features of the climate and Earth system, what that rate of change is also really important. If glaciers and ice caps melt more quickly than they might otherwise, if they melt quickly, it's going to have enormous impacts. If land cover changes more quickly or more slowly, it's going to have enormous impacts. And the strength of feedback loops in the climate are really important and really not well understood. We need to understand them better. The most important feedback loop in climate is how carbon dioxide, CO2, causes warming, because it doesn't cause warming just on its own. CO2 induced warming causes there to be more water vapor in the atmosphere. And that's what then traps most of the heat, which causes more warming. And the stronger this feedback loop is, the more warming is going to happen. And I'm presenting all of that to you because in many ways, these are all going to play out in tipping points. We're going to be moving out of the historical record into processes that we don't understand, where rates of change of how the Earth system changed are going to matter a lot because of these feedback loops. And I'll give you a few examples of what that's going to mean in terms of how the Earth might change. So what are tipping points? Tipping points are changes in the climate that are, first, typically irreversible. Once these changes have happened, we, in terms of the timescales that humans work on the scale of decades or centuries, are not going to be able to change them. They're sudden. They're going to happen in terms of changes over just a few decades, and that's going to push the climate system into these very strange places. And they're self-reinforcing. I'll give you some examples of what that means. Tipping points are situations where small changes in many cases, global warming and temperature rise lead to fundamentally different behavior in the climate system. And one of the most important changes in that behavior is that after a tipping point, every additional ton of carbon dioxide is going to cause more warming, more sea level rise, and more economic damage than before. And tipping points also push us to the boundaries of what the planet can basically maintain in order to maintain the kind of environment that humans are able to live and prosper under. I'm not going to be talking too much about that, but these tipping points are really the leading edge of ways in which the Earth system is starting to break down. To talk about tipping points, we have to do a little bit of systems thinking. So as an analogy, imagine that you're leaning back in a chair. The chair as a system has two states. State one is where you haven't leaned very far back. And if you stop leaning back in your chair, the chair is going to come forward and it's going to land on its 4 feet, and you'll come to rest in an upright position. If you keep pushing the chair back, at some point, the chair is going to push you back on its own, and you're going to fall to the floor on your back. So the tipping point in this sort of chair example is the point that we're concerned about is the point where you leaned too far back. That's the crucial moment where you've passed the tipping point. And there's an instability in this chair system that's basically based on your ability to lean backwards. So when we think of systems, in a way, the system has a mind of its own. So to just to introduce one more analogy, hopefully not too many. Imagine that you're pushing a boulder up a hill, and if you are leaning back, you push the boulder further up the hill until you get to that tipping point where the chair is balanced between leaning, falling forward and falling backward, and just a little extra push will cause runaway change. So that's the way that tipping points work in the climate system too. I'll give you two examples of this. The first one is Amazon dieback. So the Amazon rainforest is an incredibly unique and interesting place from a climate perspective, for all, aside from all the other ways in which it's incredible and unique, because the forest actually creates its own weather. It traps and recycles water into a constant mist that allows it to be such a vibrant place biodiversity-wise. So there's a feedback loop here. Tree cover causes there to be what's called evapotranspiration, which is the drying up of water into the leaves and then released in the atmosphere, which, because it's released still within that microenvironment, causes there to be rainfall, which causes there to be more tree cover in a virtuous cycle. But it turns out that rainforests, in particular the Amazon, has another state that it could be in and that we're seeing more and more often. and that is as grassland. When the rainforest gets hit by a hard drought, parts of it turn to grassland. And grassland also has a self-reinforcing feedback loop. Grassland, when it appears in a region, causes more of that rainfall that lands on it just run off onto the ground and not be useful to the trees at all, which causes there to be more drying, which causes there to be more grassland. And the grassland can spread because of this feedback loop. Even without deforestation, human-caused cutting down of trees in the rainforest, climate change harms trees, causing there to be less of this water recycling and more loss of trees, causing more of the Amazon to go into this grassland feedback loop, this second state of the tipping point. So you can sort of put that back into this boulder on a hill analogy. We're right here, perched on the edge of a tipping point. If the boulder can roll back, then the rainforest can actually heal itself. And areas where there are trees are going to make their own weather and cause there to be more trees around. If warming keeps moving forward, more and more of these grassland areas are going to expand, resulting in a lot of the rainforest going away on its own. The other example I wanted to give you is of Arctic ice cover. So as I'm sure you all know, the North Pole ice cap has been shrinking for 50 years. And mostly we're concerned here about its extent in the summer, in the middle of the summer, because it grows and shrinks every year, but its extent at the hottest part of the year tells you a lot about the health of the system. So this red outline shows where the summer Arctic sea ice boundary was in 1979, and here's where it is today. Huge amounts of loss. And it's not just the total area that's lost. The thickness of the ice has decreased enormously. So back in the 1980s here, this shows how many years old the ice is, and the longer that the ice sticks around, the thicker it gets, because every year it grows a little bit thicker. And back in the 80s and before then, over most of the polar ice cap, the ice was many years old. Nowadays, most of the ice that is representing that remaining ice cover is less than 1 year old. It was just laid down over the previous winter, and is threatening to melt away in the next summer. This is all important because ice caps cool the planet, right? If the sun falls on a nice surface of ice, most of the heat, most of the solar radiation gets bounced back into space, and you don't end up, it doesn't end up contributing to the warming of the planet. If it hits the ocean just sucks up all that warming and keeps it in the Earth system. So let's talk about these self-reinforcing feedback loops. Let's talk about the systems thinking here. There's a feedback loop where if you have less ice, then the water ends up getting warmer because more of the sun is going to be falling into the water, which is going to melt the ice from underneath. There's this local feedback loop, which is going to cause there to be less and less ice. But it's not the only feedback loop. There's also a feedback loop where if you have less ice, there's less of an area for snow to build up. And so the ice is going to be less thick, which is going to cause it to be more vulnerable to melting away. And that's not all. There's also a global feedback loop where that warmer water causes there to be a warmer atmosphere, which is going to melt the ice in addition from above. So just like with the rainforest, if you have an area that has a little bit less ice, it has the potential to to continue to degrade the ice cover. So we have this tipping point, and again, we're perched on the edge of a situation where the ice caps can recover themselves, and one in which the ice cap will dwindle away to nothing. In many ways, we're probably past this point on the tipping point, but the jury is still out. Now, those are some of the local feedback loops that cause tipping points to be tipping points. That's what causes there to be this reinforcing cycle. One of the reasons that we're concerned about them from an economics perspective, though, is when you put them in the context of the whole world and how global warming works. So the normal way that we think about the way that global warming works is you've got over here fossil fuel use, which causes there to be carbon dioxide in the atmosphere, which causes there to be warming, which causes there to be impacts like wildfires and droughts and so on. Now, I've just talked about two of those impacts, Amazon dieback and loss of Arctic ice cover. Now, these are particularly special in the sense that that they have the ability to run away on their own. Unfortunately, if they run away on their own, they also have implications for this whole process. If the Amazon begins converting itself to grassland, all of the carbon dioxide that's stored in the trees of the Amazon rainforest is going to end up in the atmosphere, causing there to be more warming. If the Arctic ice sheet melts away, causing there to be less solar radiation radiated back out into space, it's going to warm up the oceans, which is going to cause there to be more warming. And this is why, because of these tipping points, every additional ton of CO2 is going to cause more warming than the one before, because it's going to both cause the impacts that it would cause on its own, and it's going to cause these additional feedback loops to kick into action and cause there to be more warming and more CO2 that we have to deal with from them. A lot of tipping points have been identified across the globe. This is some of the most important ones. In addition to dieback of the Amazon rainforest, there's dieback of the boreal forest across Canada. There's loss of permafrost across Siberia. A very important one for Europe is the way that deep water formation forms in the Atlantic, which is crucial to the processes that keep Europe having a pleasantly warm climate. Not all of these tipping points are actually bad necessarily. So right in the middle here, there's Sahara greening, where sort of in a reverse analogy to Amazon dieback, if you get a little bit more water falling on the Sahara, you can end up with a feedback loop which causes that to produce more grassland. The grassland can start to expand across the Sahara Desert. So there are a lot of really interesting stories to be told about these different tipping points, but I'm not going to go into too many more details of them. The big questions around tipping points basically have to do with whether or not they're going to happen and where they're going to happen. So what is the likelihood of these different tipping points? The first question is, where are the trigger points? Where is the peak of that hill where the boulder is poised between these two states? Is it, for example, is it at 2 degrees Celsius, or is it below that? If we have warming of 1.5 degrees, are these tipping points already going to be triggered, or do we get to wait until 3 degrees? How likely are these trigger points going to be reached in the near term? Are we going to start to see these changes in the Amazon and the Arctic soon, and how damaging will they be if they do happen. Now, traditionally, the way that the IPCC, which just produced a new great report, has talked about these kinds of uncertainties is with what are called burning ember plots, which are shown here on the right. Typically, those burning ember plots show the risk of several different important changes in the way the biosphere or the climate is going to react at different levels of warming. But here I've just taken out the plots for tipping points from a paper that actually looked at how those levels of risk changed over 4 different reports over the last 20 years. So what this is showing you is that in 2001, the scientific consensus was that tipping points were not going to be a problem below about 2 degrees Celsius, and then they were going to gradually become more of a concern as you reach up here. By 2009, there was already an awareness that tipping points are going to start happening at and below 1 degree of warming. By the most recent report that's had these burning plots in 2018, the risk of tipping points at 1 degree is already right in here between moderate and high, and beyond that, they're essentially certain to happen. We actually, with some colleagues, went a step further using some information from what's called an expert elicitation, which is basically where a group goes out and does structured interviews with scientists to ask them, how likely do you think something's going to be? In this case, how likely do you think that the following tipping points are under different scenarios of warming? And basically, there were 3 scenarios that were discussed: a low, a medium, and high warming scenario. And they were asked about a bunch of different tipping points. This first one is those changes in how water is formed in the Atlantic, warming Europe, melt of the Greenland ice sheet, melt in the Antarctic ice sheet, and so on. And the main thing that I want you to get from this, I suppose, first is, so each of these little bars is an individual scientist's range of estimates, their uncertainty around how likely the tipping point is going to be triggered under a different warming scenario. So let's take the dieback of the Amazon down here. There's a lot of uncertainty within individual scientists' estimates and between scientists. But the other thing I want you to take away is that as you get to these higher warming scenarios, from this low warming scenario to moderate warming to high warming, the risk of these tipping points increases across the board, going from quite low, all of them below 25% chance of happening into a low warming scenario, to generally more likely to happen than not for all of them. Now, the way that we took this a step further was to just combine those and ask, well, what's the chance of at least one of these tipping points being triggered and changing the climate system irreversibly and abruptly? And what this is a sort of description of the range of uncertainty, but just look at the red line, which is the average likelihood of one of these tipping points happening, and the chance of at least one of them happening under the low warming scenario is already 75%. It's already very, very likely. If you go to a moderate warming scenario, or heaven forbid a high warming scenario, it's completely certain that we will be having these very large changes to the climate system. And these tipping points are not isolated. It turns out that when one tipping point is triggered, it makes others more likely in many cases. So for example, B here is Arctic sea ice. If Arctic sea ice essentially goes away every year, that's going to make it more likely that the Greenland ice sheet is going to melt, which is going to make it more likely that the way that warm water is formed in the Atlantic is going to change, which is going to make it more likely that the Amazon rainforest is going to die off. And because of those connections, there's this big picture perspective, which I hope I'm not bumming you all too much about this, but we have been in an amazing point in the Earth system where there's a lot of, there's been an area of stability that we have been pushing our boulder of the Earth further and further out of. If these tipping points start getting triggered on a large scale, they will start to cause the changes in the Earth to run away, and at some point hit some sort of planetary threshold, which it's theorized could turn Earth into a planet more like Venus, where all of the CO2 that's been stored in the biosphere, the forests across the Earth, is going to get out into the atmosphere, causing there to be a runaway greenhouse effect. That isn't, fortunately, a very likely situation unless we aren't able to get our act together. But it sort of points out the need for us to bring ourselves out of that pathway and toward some sort of stabilized scenario where we might not be in the regime that we were before, but we're certainly not going to let ourselves get into this hothouse Earth kind of situation. So now I want to transition to the effects of this on economics. So why should we care about economics? Well, when we're talking about climate change, we're concerned not just about the changes in the climate, but their effects on lives and livelihoods. We're concerned about making good decisions for society. And one of the ways that we can make those decisions is to think about the costs and benefits of the decisions that we make. So for example, the mitigation costs, the costs of changing our energy system are going to be borne by all of us today. The benefits of those changes to the energy system are going to be borne by future generations off into the distant future. And so how do you combine those together? How do you think about that kind of a question? Well, economics has been thinking about that for a long time. And one of the useful tools that it provides is what's called economic welfare. One of the challenges of making this kind of a social decision is that the costs of changing our energy system are going to be real financial costs, right? We're going to have to pay taxes. We're going to have to enact policies that make things more difficult financially. But the benefits aren't all going to be in terms of financial benefits. They're going to, some of them are going to be financial, but there are also going to be benefits to our health, benefits through the effects of the natural environment, the services that it provides, things that can't be easily translated into dollar terms. But it turns out that with a little bit of work, you can put these all into a common metric of economic welfare, and then compare the economic welfare of doing action and not doing action. And it's not going to be a surprise to any of you that the result of that kind of analysis is very clear at arguing that we need to do action and we need to do it quickly. There's a really tough pathway from climate to those economic outcomes. We have to think about not just what changes are going to happen in the climate system, but who's going to be exposed to them, how vulnerable those people are, and then whether those people who are impacted by each of these changes are resilient or not. If you think of say a storm that's damaging houses for a poor community, the total loss in terms of dollars of that community being devastated might be less than a similar community of rich people's vacation homes. Their total asset value might be much greater, but we need to take into account that the poor community is going to be impacted in so much more deeply a way. Their welfare is going to be lost in a very big way as opposed to the loss of welfare to rich people when their vacation houses get destroyed. A couple of things that we know about economic losses. The first is that economic damage increases at higher temperatures. So this was an analysis we did for the United States of how much welfare would be lost in terms, sort of translated into dollar terms, percent of US national GDP, across a range of temperatures. And accounting for the energy system, agricultural system, labor productivity as it's affected by high temperatures, crime, which actually responds to high temperatures, and this big blue area is the effects of health. And all of those increase as temperatures increase. The other story that keeps coming out and has been really clear in recent years is that inequality matters enormously. Poor people are the most vulnerable, and they're hit the hardest. So this is from a different analysis looking at the impacts of temperature rise on over the next century. And the richest 20% of the world is actually going to be affected in very minor ways, maybe even in positive ways, according to some analyses, whereas the poorest 20% and most of the rest of the world really will be devastated with a loss of welfare equivalent to a loss of their income of 75% or more. There is an enormous amount that we don't know. I'm going to try to click through these fairly quickly, but there's been a historical push to understand things, impacts in the market as a result of slow changes in the climate. Things like agriculture, where we have a lot of information because agriculture is bought and sold. And so people have needed to keep track of it for a long time. There's a frontier of where people are better understanding things, taking into account extreme weather and non-market impacts, things like the impact on biodiversity or health, which is a non-market impact because you don't buy and sell health, and extreme weather. We're getting a much better handle on these. But there's a range of things that we don't have a good handle on, and those include tipping points in the climate system and in the social system. Tipping points in the social system like migration and conflict, tipping points in the climate system like the ones we've been talking about, the Antarctic ice sheet collapsing or changes in polar regions. And there's also sort of an intersection of these two, like if Europe is pushed to the brink of another ice age temporarily because of changes in how the Atlantic forms its deep water. So that we can combine all of these different aspects of all the ones that we understand and some of the ones that we only somewhat understand. And there are a lot of different estimates about what that total loss in global welfare will be. But one plausible one, which we've been using recently, is based on a model that predicts that global welfare will be decreased by about 23% by the end of the century if we don't make the actions that we need to make. And that those effects are going to be worse in the tropics for a lot of poor populations. Now, I want to bring this all back to tipping points. The effect of tipping points is to add on both additional damage and uncertainty. So this is for sort of a middle of the road scenario, thinking back to the beginning of the presentation. Tipping points will increase these economic damages by another 43%. So if we were at losing 23% of global welfare, now we're up to losing about a third of global welfare. And there's a huge amount of uncertainty. So this graph shows the percent increase in a measure of those economic damages across the range of uncertainty because of these different tipping points. And the uncertainty is coming from the fact that there are a lot of aspects of these tipping points that we don't understand. There's about a 10% chance that actually the impacts of climate change are going to be double because of tipping points than those estimates that were produced before accounting for tipping points. So we're really trying to bring all this together. So does that mean for the communities that you work in that in the future everyone's just going to be 33% poor? No, not at all. There's a lot more complexity to this. First off, when climate changes in the future, and it will, whether we do mitigation or not, it's going to mean not just that on average, everyone is getting impacted a little bit more. It's going to mean more frequent disasters, more wildfires, fires, floods, and droughts, and other impacts like that. It's going to also mean impacts in things that tend to ripple through the economic system. For example, more crop failures, which is going to produce more price spikes, which is going to produce more supply shortages. And we're all going to have to be struggling and dealing with these. So those are going to happen more often in addition to, on average, just happening more. Some regions are going to be completely fine. Some regions are going to be completely devastated, and we don't know in many cases where those regions are going to be. We know that what the sort of things that matters on are how hot is it in each location already? Where is the water, and is it going to be secure in the future? What does the economy rely on? What are the industries that make it work? Are there coastal risks in a given area? So across regions, there's going to be a lot of variation. And then different groups of people are going to be impacted differently. For example, depending on what industry you're in. In particular, outdoor industries like agriculture, construction, and tourism are going to be really heavily exposed to these kinds of changes. So I think the big message from this is prepare for uncertainty. The future world is going to be less well understood because these tipping points are going to be triggered and change the way the climate system works. It's going to be more chaotic and variable, resulting in more uncertainty on a year-to-year basis. And I'd like to say that it's going to require more cooperation. I don't present that as sort of an optimistic view, though I hope that it happens, but I mean that on a person-to-person level, in order, whatever happens at the global level in terms of our ability to reduce emissions, we're going to need to work together to ensure that people can continue to live fulfilling and good lives. Now,
James, I want to make sure we have time for questions.
Yeah, so I have a number of other points that I would have gone to, but I think that this is a really good point to say sort of this is where we are. So let me just skip through a bunch of slides that we don't need. So I think that this is actually, let me stop here. So the big conclusions are there's pervasive uncertainty because of tipping points, and they're going to make mitigation and impacts both harder. Tipping points increase the losses from economic welfare by adding an extra 43% in our estimates, though with a lot of uncertainty, to those impacts. They're worse for the poor. They're going to affect lives and livelihoods globally. And finally, that we need global cooperation and local action to prepare communities to adapt to climate change and to help educate and prepare vulnerable populations to the kinds of changes that they're going to be exposed to. I think this is really the central challenge of our time. We have the potential to transform to a 0% fossil fuel, 100% renewable energy system that can produce a more equitable, healthier society. But at the same time, climate will continue to change with all the impacts that come along with it, meaning that every aspect of our lives is going to change through basically a 2-generation long society-wide effort. And I'm really glad that all of you are going to be part of this incredibly uncertain and very exciting process. So thank you so much for listening to me, and I really look forward to your questions.
And thank you very much, Dr. Rising.